simple events, okay, or simple events are collectively exhaustive and mutually exclusive. So we can call that an partition of sample space, okay. Now we consider the additive rules. The additive rules say that probability of the union between A and B is equal to probability of A plus probability of B and minus probability of A and B, okay. So you can see on the Venn diagram, we count union of A and B. We count the number of outcomes of this event, okay. So the number of outcomes of A and union B can be counted by, we count the number of outcomes of A, okay, and the number of outcomes of B. But when we do that, we already count A intersection with B 2 times, okay. We count this common part 2 times. That's why we need to subtract this part. So that gives us the formula 1.15, okay. So it's easy to prove the formula 1.18, 0.50, okay. You can say that the sum PA and PB double counts the simple events that common part between A and B, okay. So the corollary 1.1 say that when the two events A and B are mutually exclusive, that means there's no common part between the two, then we can say that the problem of the union of A and B equal to probability of A union B is equal to probability of A and probability of B, okay. That, or sometimes we can denote A union B by the notation A plus B. So we can say P of A plus B equal to P of A plus P of B, okay. And you can see on diagram, Venn diagram, A and B are two disjoint events here. And so now we can extend the additive rule for the connection of n finite mutually exclusive events A1 to AN, okay. So the probability of the union between n mutually exclusive can be computed by take the summation of each probability of each event, okay. So we can say that probability of A plus A1 plus A2 plus AN equal to P A1 plus PAN plus PA2 plus PAN, okay. And the simple corollary says that if A1 to AN is an event space, that means they are mutually exclusive and they are collectively exhaustive. Or we can say A1 to AN is a partition of a sample space S, okay. And now we see that probability of the union between the n event is equal to P of S, okay. So it is equal to 1. So that's why the summation of the probability of A1 to AN is equal to 1. And theorem 1.11 says that in the case of 3 events, A, B, and C, we can have the formula 1.19. That is the probability of the union between 3 events A, B, and C can be computed by, firstly, you take the summation between the summation of 3 probability of A and B and C. Okay, the first step is we take the summation in this way, and then we subtract the summation of the union, no, the intersection between each pair AB, AC, and BC. Okay, we subtract the summation if you take the bracket here. Okay, and then we add the probability of the intersection between A, B, and C. Okay. So if you draw the Venn diagram, so we can see that when you count the number of outcome of the union A, B, and C, then you can count by, firstly, you count each outcome of A and B and C, then you see that the outcome of the intersection between 2 events A, B, AC, and BC is counted 2 times, so you subtract that, and then you add the common part between the among the 3 events. Okay, you can draw the diagram to see that. So it's not difficult to calculate that formula. So now we consider the example 1.26. Anyone who can read out loud the example 1.6 for this? Can you? And then we summarize assumption and what we need to calculate. Who can help us to speak it out loud, please? Mr. Hoàng Trần Nhật Minh, can you?
John's going to graduate from an industrial engineering department in university by the end of the semester. After being reviewed at 2 companies he likes, he says that his probability of getting an offer from a company A is 0.8, and his probability of getting an offer from company B is 0.6. And if he believes that the probability that he will get offers from both companies is 0.5, what's the probability that he will get at least 1 offer from these 2 companies?
Yeah, that's thank you, Mr. Hoàng Nhật Minh. But can you summarize the assumption and what we need to compute now?
So the probability of getting offer from company A is 0.8. So let's say that P of A is 0.8.
Yeah.
And P of B is 0.6, and P of A united with B, which is 0.5.
Yeah, A intersection with B. Okay. Both companies. That means A and B. Okay.
So the probability of A united with B is PA plus PB, and then we will subtract to P of A united with B.
Yeah.
We have 0.8 plus 0.6 minus 0.5.
Yeah, that's correct. So now we consider an example of the solution is that we, like Mr. Nhật Minh said, we have the assumption that John gets the offer from company A is 0.8. So if we call A the event that he get an offer from company A, so P of A is equal to 0.8, okay? And we call B the event that he gets an offer from company B, so PB is equal to 0.6. And the assumption that he gets offers from both companies is 0.5, so that is probability of A intersection with B is equal to 0.5. So now we need to calculate the probability that he will get at least one offer from these two companies. What does it mean? At least one offer. That means he can get the offer from A, he can get the offer from B, or he can get both the offers from A and B. Okay, that's the meaning of the union between A and B. So we need to calculate P of A union B. Okay, so and we employ the additive rule for two events. Okay, so we use the formula from the above theorem. We get 0.8 plus 0.6 minus 0.5, and we end up with 0.9. Okay, so you can see that the probability of A union B, how can you compare the probability of A union B, probability of A, probability of B, and probability of A intersection B? Who can give the summarize on the four different probability here? PA union B, PA, PB, and PA and B. Which one is greater than the others? Which is the biggest number here? Tell. Do you understand what I asked you?
PA intersects B is largest.
Not largest one is PA intersect
B.
Really? That means A and B means this.
No. Sorry. Union.
PA union B.
Yeah.
Okay.
My mistake.
PA union B is the largest number, and then
followed by
smallest
PA.
number is
Smallest number is PA intersect B.
Yeah, PA intersection with B. Okay, and the intermediate number
PA and
PB. We cannot compare PA and PB, but we know that PA is greater than PA and B and less than PA union B. Okay, A plus B, we can say that. I repeat, PA and PB, we cannot compare the two probability, but we say that PA and PB is greater than PA and B and less than PA plus B. Okay, that's the order that we can give. Okay, and the theorem 1.12 is very easy. We know that A and AC are complement. So we have the probability of A and B summation gives the number 1. Okay. So now we consider an example 1.27. Who can read it out loud first and then summarize the assumption? Yeah, Mr. Nguyễn Tống Minh, please.
Now we have the event that he will serve at least 5 car a day. So now we consider its complement of the complement of this event, and the complement of this event, he will serve 3 car a day or 4 car a day. So I sum up its the probability of the this.
No,
It will be the.
Can you slow down a little bit? Can you summarize the assumptions here, and then what do we need to calculate?
Yeah, the first thing is that I will consider the complement of the event that he will serve with at least 5 cars. So that's the complement of this event will be the event that he will serve 3 cars a day or 4 cars a day.
Yeah.
So I will sum up the probabilities of 3 and 4. It will be 0.31. Okay, 0.31. And then, as we know about the theorem, the last bit theorem, we will minus it with 1, and we will have the probabilities of the event.
Yeah, in fact, we can count in the different ways. Okay, the first way you can compute the probability of the event that at least 5 cars are survived. Okay, are served, and less than at least 5. What does it mean? Greater or less or equal to 5? So we have 2 or 3, 4, 5, 6, 7, and 8. So greater or equal to 5. What does it mean? What that means? We have 5 or 6 or 7 or 8. So we have 4 different cases. Okay. But now, if we use the complement rule, so we can count the probability of getting less than 5 cars. Okay, so that is 3 or 4. So we count instead of count 4 cases, we count only
2 cases.
2 cases. Okay, 2 cases, and then we use the complement rule. But in fact, we also need to compute 3 times. Okay, 3 computation here. So in fact, 3 compared to 4, it doesn't matter. Okay, it's not really different. But sometimes if we need to count a lot more cases, then we can count the complement event that has less cases than the original event. Okay, that's what we need to do, and here it's very convenient to count both the cases. Okay, it doesn't matter here, and we can generalize the addition rule for finite event A1 to AM, but in fact we need only 3, or maximum is 3 events. Okay, so we don't need to remember the general case in 1.21, but anyway we have this formula. Okay, for anyone who care more about the addition rule. Okay, so firstly we take the summation of one event. Okay, a probability of one event, and then we take the subtraction of the probability of 2 events. Okay, and then we take the sign plus sign with summation of probability of 3 events, and so on. Okay, you can see here the negative sign is followed by the positive sign here. Okay. And then the theorem 1.14, what does it mean? It means that any event A can be split into different small parts, which is the intersection of A and each event in an event space B1 to Bm. That, what does it? We can show the Venn diagram to see it more clearly. For example, here, partition. That's the partition. Here later. A bit here. Yeah, the meaning is that, for example, we have the sample space S, and then the sample space is split into different parts, B1 to Bm. So now an arbitrary event A can be split into small part, A intersection with B1, A intersection with B2, and A intersection with Bm also. Okay, so that's why sometimes we can compute the probability of event A by take the summation of smaller probability of P A intersection with Bi. Okay, we take the summation from 1 to m here. Sometimes it's very useful. Okay, and it's not difficult to calculate the formula 1.22. Okay, and now we move to the conditional probability and the concept of independence, and we consider also the product rule. We have already additive rule, and now we consider product rule. Okay, so the definition of conditional probability I have already said. For example, assume that the probability that a regularly scheduled flight departs on time. We denote it by PD, and it is equal to 0.83, and the probability that it arrives on time is PA. You see, at the beginning we consider the event of departing on time, and now we consider the event that it arrives on time. Okay, so PD is equal to 0.83 and PA is equal to 0.82. Okay, you see, departure and arrival. Okay, and now we assume that the probability that it departs and arrives on time. That means it departs on time, and then it arrives on time also. Okay, at the same time. D intersection with A. This probability is a little bit smaller. Okay, you see, we know that the probability of the intersection between the two events is always less than PA and less than PD. Okay, so it is 0.78, and now we need to find the probability that a plane arrives on time, given that it departed on time already. Okay. Okay. The first case, the part A, we need to compute the probability that a plane arrives on time, given that it departs on time already. Okay. So at the beginning, we know that we call, for example, where it departs at Nội Bài Airport, for example, and we call the Ho Chi Minh, the destination at Ho Chi Minh City, for example. We call that, yeah, this plane is already departed on time. Okay, and then we consider the probability that the plane arrives on time at Ho Chi Minh City. Okay, and now we also consider the part B, that given that it arrived on time. So, for example, at Ho Chi Minh City, we know that it arrived on time, and now we consider the probability that it departed on time at Hanoi. Okay, that's the meaning of this example, and the solution is that we consider the PA given D. D is departure on time and A is arrival on time. Okay, so now we use the definition of conditional probability. It is equal to PA intersection with D divided by PD. So now you can see that is the fraction of 0.84.78 divided by 0.83. So you get a bigger probability. Okay, so given that it departed on time, the probability that it arrives on time is very big. Okay, nearly 1. Okay, and now the inverse probability given A, now given A, so we compute the probability of D. Okay, and we use also the definition of conditional probability. So now we have a fraction of 0.78 divided by 0.82. So we have also a very big probability. Okay, and it's a little bit bigger. So anyone who can answer the question that can you tell the order between PA given D and PD given A? Is it comparable? Can we always say that this one is greater than this one, or this one is less than this one? Who can answer this question, please? Any volunteer? I mean, can you compare PA given D and PD given A or not?
No, we can't always compare because it depends on PA and PD too.
Sure. That is not comparable. We cannot say this value is greater or less than this value. It can be greater than, or can be less than, or can be equal. We don't know. Okay, we never know. Okay, it depends. Here you see that PA given D is 0.94 and this PD given A is 0.95. Yeah. So in this case, PA given D is less than PD given A. But if we change the assumption, so then PA given D can be bigger than PD given A. It depends on the assumption. Okay. We consider another example. Consider an experiment that consists of testing two integrated circuits that come from the same silicon wafer. So we see the circuits on, for example, the main board of a personal computer or the PC, okay, and observing in each case whether the circuit is accepted, okay, or rejected. We denote the event that it is accepted as A, and the event that it is rejected by R. And now we consider a priori probability model. Priori, that means it is given, okay? We know that that's the provided information before we consider the probability, okay? And we say that P reject is 0.01 or 1%, okay? 1%. That means the probability of the event that the two circuits is rejected is only 1%, okay? And the probability that the first one is rejected and the second one is accepted is also 1%. And the probability of the case that the first one is accepted but the second one is rejected is 1% also, okay? The three probability are equal to 1%, and the probability of the first one is accepted and the second one is accepted is very big, okay, 0.97. And now we need to find the probability of the event B, which is the second chip is rejected, and the event C is that the first chip is rejected. And we also need to find the conditional probability that the second chip is rejected, given that the first chip is rejected, okay? So the solution is that we compute the sample space of the experiment, and we know that we have 4 different cases, okay? Reject, accept, accept, reject, accept, okay? So we have 4 different outcomes of sample space here. And what is the event B? Second chip is rejected. So we have 2 different disjoint event here. Reject, the first reject, okay, and the first accept, given that the second is rejected, okay. So we consider two cases. First is reject and first is accepted, okay. So we use the additive rule to compute that PB equal to PRR plus PAR, okay, and we get the probability of B is 2%, okay, 2%. How about C? C is, what is C? C is the first chip is rejected, okay. So we consider 2 cases, 2 disjoint event. The first one is rejected, so the second one can be rejected or accepted. So we use also the additive rule to get the probability of C is 2% also, okay. And now the conditional probability of the second one being rejected, given that the first one is rejected already, okay. So that is the PB given C, and we compute by divided PC to PC, and we get the probability equal to 0.5, and the probability of B and C, that is both of the two circles are rejected. Okay, so we compute RR is 0.01. Okay, and now you can think about the example 1.30 at home. Okay, and you can give me the answer for this example after the class. Okay. Now we consider the notion of independent events. Now we consider the two events A and B in the same experiment, for example, and we say that they are independent if and only if the probability of this event is not influenced or changed by the occurrence of the other events, and vice versa. Okay, what does it mean? The definition. That means that the probability of A given B or B given A does not depend on the condition. Okay, or in other words, we say PA given B, PA given B in here is equal to PA, and PB given B, PB given A is equal to PB. Okay. In fact, we need two conditions here, but you can easily prove that if we have only one condition, then we can derive the other condition. So the definition says that we need both of the two equality here, but in fact we can prove that if we have only one equality, then we can derive the other one. Okay. For example, we consider the experiment that we toss a single die 2 times. So you know that the die has a 6-sided, okay, 6 sides, and each side have dot on the face. Okay, so we have 1 dot, 3 dot to 6 dots. Okay, and now we toss a single die 2 times and consider the two events. A is the event that we observe the we observe 2 on the first toss, and B is the event that we observe 2 on the second toss. Okay, so the probability of A is 1 over 6. Okay, and the probability of B is also 1 over 6. Okay, the first case, the first experiment does not influence the second experiment. Okay, so no matter the first toss is 1 dot, 2 dot, or 6 dot, so the second toss is, we can observe 1, 2 to 6 also. So it doesn't matter the first case. Okay. So the PB given A is also 1.6, 1 over 6, and PB given A is also 1 over 6. Okay. And theorem 1.15 says that if an experiment of the two events A and B can both occur, then we can compute the probability of the intersection of A and B by multiply PA with PB given A. Okay. Provided that PA is greater than 0 cos. Okay. Or you can compute it by the other way. You can compute by PB multiplied by PA given B. So we have two ways to compute the probability of A intersection with B. Okay. That is the multiplicative proof, or we can say the product proof 1.26 or 1.27. And in a special case, when A and B are independent, we know that PA intersection with B, now it is equal to PA multiplied by PB. So we can say that in another word, PA multiplied by B is equal to PA multiplied by PB. Okay. I repeat, P of A multiply. We can use the sign multiply here. Okay. A multiplied B. We say that PA multiplied by B is equal to PA multiplied by PB. Okay. That's the formula 1.28 says. For example, we toss two coins at the same time, okay, and observe the outcomes. We consider event A. The first coin is headed, okay, and the event B, the second coin is tailed. So we will see A and B if they are independent or they are dependent. So we see that the sample space is HH, that means head for the first toss and head for the second toss, okay? Or HT, first H for the head for the first toss and tail for the second toss, okay? Or TH or TT, we have 4 different outcomes. And now we consider PB, PA and PB. PA is easy to compute, okay? PA is 1 over 2, and PB is also 1 over 2. Here we have 2 outcomes for A, okay, and 2 outcomes for B also, okay. So that is PB is equal to 1.1 over 2. And how about PA and B? A and B, what does it mean? A is head for the first coin, okay, and B is T for the second coin. So you see, A and B, that means the first coin is head and the second coin is tail. So we have only H, T here, only 1 outcome for the event A and B, okay. So the probability of A and B is equal to 1 over 4. And we now take the multiplication of PA and PB. That is 1 over 2 multiplied by 1 over 2 So it is 1 over 4, and it is equal to PA and B. So we can say that the two events are independent. Okay. And now before we give the definition of the two events independent, but now we consider the case that the three events are independent. Okay, so what is the definition says? What is the definition saying? First condition is that each pair of the three are independent. That means A1 and A2, A1 and A3, A1 and A2 and A3, A1 and A3. So that means each pair of them are independent. We have three cases here: A1, A2, A1, A3, and A2, A3. Okay. And the fourth condition is that the probability of the intersection of three events is equal to the product of PA1 to PA3. Okay, so we see that we need not only the pair, but we need the intersection of three also. Okay, we consider also at the same time the three events. Okay, so we take an example 1.35. We can consider the sample space S equal to 4 outcomes. We number it as 1, 2, 3, 4. With each event is equally likely, so we have PS equal to 1 over 4 for all S belongs to S. Okay, small s belongs to big S. And now consider the event A1 with 3 outcome 1, 1, 3, 4, and the event A2 with 3 outcomes 2, 3, and 4, and the event A3 is impossible event, okay, or empty set. So we need to answer if the three events A1, A2, and A3 are independent or not. Okay, so we consider 4 conditions. For the pair between A1, A2, and A3, we have here P1 and A1 and A2 is we can see the common part is A1 and A2 is 3, 4. Okay, so it is 1 over 2 here, and so it is different from the multiplication, the product of PA1 and PA2. Okay, PA1 is 3 over 4, and PA2 is also 3 over 4. Okay, so we see that it is not satisfy the condition of PA and A1 and A2 is not equal to PA1 and PA2. So we say that the three events are not independent. But the interesting part is here. You see that the probability of the intersection of A1, A2, and A3 is equal to the product of PA1, PA2, and PA3, and it is equal to 0. But this pair A1 and A2 are not independent. Okay, you see that A1 and A2 are not independent. Okay, so we give the definition for the case that we consider more than 3 independent events. In general, we consider the set A1 to AN. We say that the set A1 to AN are independent if and only if every set of n minus 1 set taken from A1 to AN is independent. That means we consider only n minus 1 set. Okay. For example, A1 to AN minus 1 or A2 to AN. Okay. And we say that every set of n minus 1 set taken from this collection is independent. Okay. And we say that the second condition is the probability of the intersection between the n events is equal to the production of PA1 to PAN. Okay. What does it mean, the first condition here? The first condition say that for the definition of n independent events, we need the definition of n minus 1 independent events. Okay. So for the definition of n minus 1 independent events, okay, we need the definition of n minus 2 definition, the definition of n minus 2 event independent. Okay, and n minus 2 we need n minus 3 independent events. That means we go back to the definition of the case 3 and then the case 2. Okay, you see that the meaning of the first part is that we, for example, we consider 10 independent events, so we need to know the concept that 9 events are independent or not, and then for 9 events we need to consider if 8 events are independent or not. Okay, and then we need to consider the beginning. The first step is two events are independent or not. Okay. So the remark 1.6 says that this definition in the example 1.35 show us that when n is greater than 3, it is a complex matter to determine whether or not the set of n events is independent or not. Okay. On the other hand, if we know that a set is independent, it is a simple matter to determine the probability of the intersection, okay, of any subset of the event. That means any subset can comprise 2 or can comprise 3 or can comprise 4 events taken from the n events. Okay. For example, theorem 1.17, we consider n events from A1 to AN. Okay, and then we can extend the multiplicative rule to the formula 1.29. Okay, that means to compute the intersection, the probability of intersection A1 to AN, we now split it in simple cases. Okay, first we compute the probability of A1. Okay, and then we take the conditional probability of A2 given A1, and then we take the conditional probability of A3 given A1 and A2 occurred already. Okay, first I repeat, first step we consider probability of A1, then we consider the probability of A2 given A1, okay, and then we consider the probability of A3 given A1 and A2, okay, and so on, so on. And in the special case, when the connection of A1 to AN are independent, so we say that we have the result the 1.30, that the probability of the intersection A1 to AK is equal to product of H A1 to AN. Sorry for the mistake here. Probability of P of A1 intersection to A2 intersection to AN here is equal to PA1 multiplied by PA2 multiplied by PAN. Okay, that is general case when the n events A1 to AN is independent. Okay. For example, we consider an experiment that the three cards are drawn in succession without replacement. That means you take first, you take one by one. Okay, you take the first card and we move it out, and then you take the second card and you set it aside. Okay, you set it aside, and then you take the third card, then you set it aside. Okay, and now we find the probability that the event A1 and A2 and A3 occurs, where A1 is the event that the first card is red ace, A2 is the event that the second card is rank 10 and or jack, okay, 10 or jack, or we can say G, okay, and the A3 is the event that the third card is greater than 3 but less than 7. Okay, let's consider that probability. So what is event A? The first card is red ace. So we have how many red ace here in the 55 card of deck? Okay, have a deck of 55 cards. So we have two red aces. Okay, and so the probability of P of A1 is 2 divided by 52. Okay, and the second card, the A2 is the second card is 10 or jack, given that the first card is red ace already. Okay, so we can easily compute this probability. Okay, we have 4 cards rank 10. Okay, and we have 4 cards rank 4 jack card. Okay, so we have in total 8 outcomes for the event A2. Okay, and for how many we have how many cards left? The remaining cards, it has only 52 cases. Okay, we have only 52 cards remaining. Okay, so the probability of A2 given A1 is 8 over 51. Okay, and now we consider the conditional probability of A3 given A1 and A2. Given A1 and A2, what does it mean? The first card is already red ace, okay, and the second card is 10 or jack, okay. So the third card is greater than 3 or less, but less than 7, okay. So how many cases, how many outcomes for this? Okay, for this event, we greater than 3. That means we can have the card rank 4 or 5 or 6, okay, greater than 3 and less than 7. So we have 3 cases, 3 ranks multiplied by 4 in each rank. So we have 12. We have 12 outcomes, okay. And now, because we have already taken the first card with red ace and the second card with 10 or jack, so we have only 50 remaining cards, okay. So the probability in this case is 12 over 50, and now we compute the probability of the intersection of A1 to A2 and to A3. So we use the product rule or multiplicative rule. A1 first step, and then second step we conditioning on A1 with A2, and the third step we conditioning A3 with condition on A1 and A2, and we have the answer 8 over 5,525. Okay, that's what we apply the multiplicative rule. Okay, so I think we need to have a 10-minute break. Do you want to have a 10-minute break? Hey guys, where are you?
Yes.
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 And then if you have any questions, we will see, okay? So we will return at 11:05, okay, 11:07. Okay, hello guys, where are you? Let's return to our lesson. Okay, so we and now we consider base rule. We move to base rule. It is very interesting theorem. Okay, let's continue. We consider remark 1.7. It is about the difference between mutually the concept of mutually exclusive and the concept of independence. Okay, can we derive this concept to the other? Okay, so let's see that when the two events are mutually exclusive or disjoint, they cannot both happen. Okay, that's the definition of mutually exclusive or disjoint event. So once the event B occurred, the event A cannot occur. So the probability of A given B is 0. Okay, and vice versa. That means the occurrence of event B certainly affects the probability of event A. Okay, therefore, if the two events A and B are mutually exclusive, they must be independent. Okay, that means mutually exclusive means that they are not independent. Okay, they are dependent. Okay, and how about the case when the two events are independent? Can we derive that they are mutually exclusive? Then the question, the answer is no. We don't know if the two events are independent. We don't know if they are mutually exclusive or not. Okay. So you see, when the two events are independent, we only see that P of A and B is equal to PA multiplied by PB. So the probability of the union of A and B is now PA plus PB minus PA multiplied by PB. So we cannot cancel out this part. So that means they can be disjoint, or they can be not disjoint also. Okay, we don't know about this part. Okay, if they are disjoint, so this part must be 0. But here, when they are independent, we don't know that. That means from the independence events, we don't know if they are mutually exclusive or not. But from the mutually exclusive events, we say that they are not independent. That's for sure. Okay, so we should not mix the two notions. Okay, mutually exclusive is very different from independence. Okay, that's the remark 1.7. And now we move to the very interesting theorem. We can say that theorem is Bayes' rule, or we can say Bayes' theorem. And from this very important theorem, they even set up the new approach of the statistic. We can say that we have two different approaches for statistic. One is frequentist approach, and the other is The other is Bayesian statistic. So we can search that term on the internet. Okay. And now, what is, before going to the Bayes rule, we consider the law of total probability. Okay. So theorem 1.18 says, consider the event space B1 to Bm, or we can say the connection. This collision is a partition of the sample space. Okay, and each part here has a probability, positive probability. Okay, and now we consider event A. So we can compute the probability of event A by conditioning on each part. Okay, so the formula 1.31 says that to compute proper PA, we can compute PB1 and multiply by PA given B1. Then we compute PB2 and multiply by PA given B2. Then, and so on, we compute the probability of PM multiplied by PA given BM, and we take the summation of each part here. Okay, so we can use the other notation as in 1.31.1. Okay, so to compute the probability of RA, we can split it into a partition of A, that is A given B1 or A given B2. In fact, A and B1, this part, you know that we know the product rule of probability. PB1 multiplied by PA given B1, that is PA and B1. Okay, and here PB2 multiplied by PA given B2, that is the probability of A and B2, or intersection with B2. You know that? Okay, so that is the other way to compute the probability of A, by split it into small parts, different small parts, or different or partition. Okay, A and B1, A and B2, and A and Bn, and then we use the product rule to have the formula 1.31. Okay, here that's the Venn diagram to illustrate the formula 1.31. Here we have a partition of sample space. Okay, B1, B2, B3, Bm, and we consider an arbitrary event A. So the event A can be partitioning into different parts by A intersection with B1. Okay, A intersection with B2. Here is the empty set, but in general we can say that A intersection with B2 also, and A intersection with B3 here, A intersection with B4. That's empty set here. No, not in empty set. Here is this part. Okay, A intersection with B3, B5 here. It's small part here, and A intersection with Bm, for example, this part. Okay, so A can be split into, in this case we have 1, 2, 3, 4, 1, 2, 3, 4, 5 parts here. Okay, so probability of A is equal to probability of A and B1, A and B2, A and B3. But then we apply the product rule probability. So we conditioning. First step is probability of B1. Okay, and then the conditional probability of A given B1, then probability of B2 multiplied by conditional probability of A given B2, okay, and so on. That's the meaning of the formula 1.31, okay. The proof is very simple, so you can see the proof at home. Okay, you can read it after. And we consider the example 1.37. A company has 3 machines, B1, B2, and B3, for making 1 kilo ohm resistor. Okay, so we just care about the 3 different machines to produce the resistor here. Okay, that's the type 1 kilo ohm resistor. So that means if we randomly choose one resistor from this company, so it can be made by machine 1 B1 or machine B2 or machine B3. Okay, and then we can denote B1 is the event that the resistor is made by machine 1. B2 is the event that the resistor is made by machine 2, and B3 is the event that the resistor is made by machine 3. So we have 3 different cases, okay, at the beginning. We know that. So we call that the prior information, okay. And now we observe from the prior information. Now we observe, okay. We know that, but we haven't observed anything, and now we observe. We observe what do we observe now? We observe that 80% of resistor produced by B1 are within 50 of the nominal value. That is the set of critical, okay, critical value. So that is, you need to satisfy 50 nominal value to pass the check. For example, if you want to export to or to commercialize the products, you need to satisfy 50 nominal values. Okay, if you don't pass one of the nominal values, so you cannot commercialize your resistor. Okay, so they say that only 80% pass the test. We can say that. Okay, 50 nominal value, we don't care about that. We just say we need to test. Okay, and from the experience, we say that only 80% of resistor is accepted. Okay, if it is made from machine B1, and for machine 2, the percentage is a little bit higher. Okay, 80% is accepted. Okay, and for the machine 3, it is very low, only 60%. That means the machine B, the machine 2 is the best one. Okay, and the machine 1 is the intermediate one, and the machine 3 is the worst machine. Okay, now we say that in each hour, machine 1 produce 3,000 resistors, machine 2 produce 4,000 resistors, and machine 3 produce 3,000 resistors also in each hour. Okay, and now they mix all the resistors together and randomly. Okay, mix randomly, in one bin and packed for shipment, okay, to commercialize. So now we ask, what is the probability that the company ships a register that is pass the test? We can say that within 15 of the nominal value. That means what is the probability that the company ships can pass the test? Okay. So to make it more clear, we denote A, the register pass the test. Okay. So we need to compute PA. Okay. Register is within 15 of the nominal value. That means pass the test. Okay. B1 is, that's what I said before. The product is made by machine 1. B2 is product is made by machine 2, and B3 the product is made by machine 3. Okay. So you can see that B1, B2, and B3 is an event space or partition, because there's no other cases. Okay. There's only 3 machines. So each register must be made by B1 or B2 or B3. There's no other cases. Okay. So we can use the law of total probability to compute PA. We split it in 3 parts. First part is PB1 multiplied by A given B1. Second part is B2, and the third part is B3. Okay. So how can you derive the prior information into formula? So you know that B3 produced 3,000 resistor out of 10,000. So the probability of getting a product from machine 1 is 3,000 divided by 10,000. Okay, that's 30%. Okay. So for machine 2, it produced 40% of the products. Okay, and for machine 3, it produced 30% of the products also. And now, how about the conditional probability of A given B1? Given that the resistor is made from B1, we know that the probability that it passed the test is, you know, that 80%. Okay, from the assumption 80% of resistor produced by machine 1 pass the test. Okay, so that means PA given B1 is 80% or 0.8, and given a resistor made by machine 2, it passed the test with the probability of 90%. Okay, the second machine is the best one, and the third machine is the worst one. Okay, with only 60% product pass the test. Okay, and now you replace all the value of each event and conditional event into the formula of PI. You get the answer 0.78. That is the probability in general. If you mix all the product within a bin and pack it. Okay, and now if you conduct the test, so the probability that the one product from that bin pass the test is only 78%. Okay, for the whole factory. Okay, yeah, that's the meaning of the total law of total probability. So Here you cannot compute PA directly by apply the definition, classical definition. Okay, you cannot count all the outcome of A divided by all the outcome of the whole factory. We don't know. In fact, the whole factory we don't know. Okay, of A. So for practice test, you can do it at home. Okay. And now we move to the Bayes rule, a very famous and very important theorem. Sometimes we say Bayes rule, sometimes we say Bayes theorem. It is a theorem, okay? So this theorem, in fact, is very easy to derive, but the meaning is very meaningful, I think. Yeah. For example, if you want to compute the probability of B given A, now you can inverse it by compute the probability of A given B, and now you multiply by PB to get the probability of A and B. Okay, that's a probability of intersection between A and B. Okay, and now you divide that value to PA. Okay, so this formula says that to compute the conditional probability given A, you can now compute the conditional probability given B. Okay, so you inverse the conditioning here. Okay, to prove this, it is very easy. You can do it at home. And sometimes they call that A is the information or the evidence. B is the posterior probability given evidence. And now at the beginning we know that the prior information about B. For example, you know PB, that is prior information. And you know that the conditional probability of A given B. Okay, and you know the probability of A. And now you can inverse the conditioning. So we say that PB given A, that is posterior probability, and PB is prior probability, and PA given B, that is the probability of what we observe here. A is what we observe, and B is what you have the prior information. Yeah, that is assumption, for example. And now you observe A with this probability, and then now given that you know the observation A, now you compute the posterior of B given A. Okay, that's the meaning of Bayes theorem. And apply also, because you know that PA can be computed by applying the law of total probability. So the other form of Bayes theorem is here in formula 1.33. So instead of compute PA directly, we split it into small part to take the summation. Here we have already do that before. Okay, that's the numerator is already the law of total probability. Okay, and the denominator, you know that B1 BI, for example, multiplied by PA given BI, that is the probability of the intersection between A and BI. Okay. Yeah. So in case of we have an event space B1 to Bm, so we can now at the beginning we know the probability of B1, B2, Bm. That is prior information. Okay, and we know that the probability of observe A given BI. We know all that prior probability, okay? And now, if A occurs, that means we have an observation of A, okay? Then now we can compute the posterior probability of each part of the partition, okay? B1, B2, and Bm given A, okay? And we know that, you know that the summation of B1 given A plus B2 given A plus Bm given A is equal to 1, of course, okay? So that is, or we can also say, if we can put all B1 given A, B2 given A, you have another partition of A, okay? You have another partition of A. Proof is very easy, so you can read it at home. Now let's consider example 1.39. Okay. We take the example 1.37 about the shipment of resistor before. We have already said about that. Okay. Now we learn that the probability that a resistor is from machine B3 is B3. That's the 30%. We know that. Okay. And we know that the probability that a resistor is accepted, okay, that is pass the test is PA equals to 0.78. And now, what if you observe that we can see the mark from the resistor, okay? Every resistor need to be marked, okay? So for example, if it is marked by, it is made by the machine 3, so it is marked by B3, for example. You have a sign on that resistor. So if you take it, then you observe it. So you know that, given that a resistor is from machine B3. So what is the conditional probability that it is accepted? Okay. You know that if it is from machine 3, the probability that it is accepted is only 60%. But now you want to see that, you want to know that if it is accepted, what is the probability that it is made from machine 3? Yeah, that's what we care about. Oh, do you mean what I am saying? At the beginning, you know that if it is made from a machine 3, so the probability that it is accepted is only 60%. Okay, but now, for example, you don't see the mark anymore, so you just know that it is accepted. So what is the probability that it comes from machine 3? Okay, yeah, that's the interesting question also. For example, one man who take one resistor from the bin, okay, and then he said, yeah, it passed the test. So you don't know the mark. You don't know if it is made from machine 1 or 2 or 3. So now he asked, what is probability that this acceptable resistor comes from machine 3? And he can, of course, he can ask, what is probability that it is made from machine 2? It is made from machine 1 also. He can ask any probability from that. Okay. So now we have a solution for that example. We use Bayes theorem to get that probability of B3. That is the resistor comes from machine 3. Okay, and given that it is acceptable already. Okay, and now we apply the Bayes theorem. We inverse the conditional probability A given B3 multiplied by probability of B3 divided by probability of A. Okay, we already have this quantity. Okay, this quantity is 0.78. We compute it before. Okay, and we know this value also. P of B3 is 30%. P of A given B3 is 60%. So we replace the quantities into the formula. So you get probability of B3 given A is only 23%. So at the beginning, you know that without the information, it is acceptable or not. You know that P of B3 is only 30%. Remember that B3 is 30%. That means the machine 3 produce 30% of the product out of 10,000. Okay, but now given the information, the new information, that it is acceptable, so the probability now decrease to only 23%. So you see why it happens. Can anyone who can explain why it happens? Mr. Hoàng Trần Nhật Minh says the naive Bayes theorem classifier in machine learning. It is fastest one, but it is not very exact. Okay, so when you apply the first one, that means it can have big errors. So it's normal. If you want to improve the precise, okay, so you need to do it more carefully. So that means the algorithm when reduce a little bit longer. Okay, so that's easy to understand. Okay, so when you use naive Bayes theorem, that is you apply that the Bayes theorem in general with no assumption. Okay, no assumption. So that's why it runs fastest. Okay, so can anyone who explain this case why at the beginning we know that PB3 is 30%, but now with the new information the probability decrease into only 23%. Why it happens? Anyone? One who can answer this? Yeah, it's not difficult to explain, to interpret. Why? Because now it's not a random resistor, it's the acceptable resistor. Okay, so you know that if it is acceptable, that it passed the test, so it is more likely to come from the machine who produce the better quality. Okay, so we see that the machine, the assumption is that the machine, you see the machine 1, no, this not this one. Okay, the machine 1 produce 80% of good product. Okay, machine 2 produce 90% of good products. So good, that means acceptable. Okay, and the machine 3 is only 60%. So what does it mean? What does it mean? It means if we consider a good one, so it's more likely to come from machine 1 or machine 3 more than more likely than comes from machine 3. That's why if you have the new information that the product is acceptable, so now the probability that it comes from machine 3 decrease, okay, into 23%. And now for machine 1, it increased a little bit, okay. At the beginning it's 30%, but now it's 31%. And for the machine 2, at the beginning it is 40%, okay. Beginning we have 30%, 40%, and 30%, but now you have 31, 46. This increase a little, this increase a little, but this one decrease, okay. Yeah, it's understandable, okay. And now you have the new distribution. At the beginning you have 30%, 40%, 30%, but now with the new information you have 31%, 46%, and 23%. So it rearranged the distribution of product. Okay, that's very interesting, right? So that's why we say that the probability depends on what you have new information. Okay, and that's very interesting and very sophisticated part of probability. Okay, so for practice test 2, you can do it at home. Practice 3 also. And I think that's enough for today. For Bernoulli trial calculator, I think you can read it at home because it's not difficult. So, any questions about today's lesson? Any question, guys? Where are you? I cannot see or hear anyone from you.
Thầy có thể đưa bài tập vào assignment được.
Yeah, I will do it after. Okay. And next week, I think we will do some homework instead of giving a new lecture. Okay. Because you have the distribution of this syllabus is 2 hours for lecture and 1 hour for practice, okay, for homework. So that's why I have already reviewed 2 lectures. So next week we will do some homework, okay. Anyone who want to ask any question? So you need to feel free to ask. Don't hesitate. Okay, I will give you some more exercise, some quiz also, so you can do it at home. Okay. So if you don't have any more questions, so I will stop the lecture today. Okay. So see you next week, guys. Enjoy your week.
Cho thầy.
Thank you. Thank you for listening.
Em thầy.